Ever wonder how a helicopter manages to stay in the sky with such precision? It's not just a marvel of engineering but also a testament to the power of mathematics. This intricate balance of flight is maintained by something known as the helicopter total algorithm. This mathematical model is the invisible force that keeps helicopters aloft, allowing them to perform complex maneuvers with remarkable accuracy. It's like the conductor of an orchestra, guiding every part to work in harmony. Without it, the symphony of flight would be a cacophony of chaos. The helicopter total algorithm is paramount in the realm of aviation, playing a critical role in controlling and maintaining the flight of these incredible machines. Understanding it not only unveils the mystery behind how helicopters fly, but also provides a fascinating insight into the beautiful complexity of aviation mathematics. Intrigued yet? Good, because it's time to delve deeper. Let's delve into the components of this intriguing algorithm. The heart of the helicopter total algorithm lies in the rotor system. This crucial part of the algorithm is inspired by the very anatomy of the helicopter itself. The rotor system, with its spinning blades, is the heart that pumps life into the helicopter, and it's no different in our algorithm. The rotor system is a complex beast, but fear not. It's all about understanding two key aspects: lift and thrust. Lift, in the simplest terms, is what propels the helicopter upwards, defying gravity. On the other hand, thrust is what pushes it forward, slicing through the air like a knife through butter. Now, how do we model this in our algorithm? It's a blend of physics and mathematics, a symphony of numbers and equations. The lift is modeled using a principle called Bernoulli's principle, which states that an increase in the speed of a fluid occurs simultaneously with a decrease in pressure. In the case of our helicopter, the air is the fluid and the rotor blades are speeding it up, thereby creating the lift. Thrust, on the other hand, is a bit more straightforward. Newton's third law of motion tells us that for every action, there's an equal and opposite reaction. So, as the rotor blades push the air down, the helicopter is propelled forward. But it's not just about these two forces. The rotor system also has to account for factors like air density, rotor speed, and the angle of the blades. These variables are all woven together in a complex mathematical tapestry that is the rotor system algorithm. This algorithm is a dynamic entity, constantly adjusting and recalculating based on real-time data. As the helicopter ascends higher, the air density changes, and so does the rotor speed. As the helicopter tilts forward, the angle of the blades changes. All these changes are continuously fed into the algorithm, ensuring the most accurate simulation of a helicopter's flight. The rotor system is the backbone of the algorithm, but there's more to it. The rotor system may be the heart, but it's just one part of a larger, more complex organism that is the helicopter total algorithm. So buckle up as we dive deeper into the fascinating world of helicopter algorithms. Now that we understand the rotor system, let's move on to the control system. The control system is the nerve center of the helicopter total algorithm. It's where the pilot's inputs get converted into tangible actions or effects on the rotor system. But what exactly does this involve? To start with, the control system is responsible for interpreting the pilot's commands. These commands could be anything from a simple change in altitude to a more complex maneuver like a sharp turn or a sudden stop. The control system takes these inputs and translates them into a language that the rotor system can understand. Think of it like this: the pilot is the conductor of an orchestra, and the control system is the sheet music. The conductor can wave his baton all he wants, but without the sheet music to guide them, the orchestra won't know what to play. Similarly, the pilot can manipulate the control stick and rudder pedals, but without the control system to interpret these movements, the rotor system won't know how to respond. But the control system does more than just translate. It also models the effects of these inputs on the rotor system. This involves a complex set of equations that take into account various factors such as the helicopter's current speed, altitude, and orientation, as well as the properties of the rotor system itself. For example, if the pilot wants to make a sharp turn, the control system will calculate how much to tilt the rotor disc, and in which direction to achieve the desired effect. It will also consider how this action will affect the helicopter's stability and balance, and adjust the rotor speed or pitch accordingly. In essence, the control system is the brain of the helicopter total algorithm. It's the part that allows the helicopter to respond to the pilot's commands in a precise and controlled manner. It's what makes a helicopter not just fly, but fly in the way that the pilot intends. The control system is where the pilot's inputs are transformed into action. The dynamic system is where the action happens. So let's dive right into it. The dynamic system is the beating heart of the helicopter total algorithm, governing the way the helicopter moves and responds to control inputs. Picture it as a grand symphony, where each instrument plays a crucial role in creating a harmonious tune. The dynamic system is the maestro, directing each part to create the helicopter's seamless flight. Now let's talk about the mathematical components that model this system. While it might sound intimidating, it's actually quite fascinating. The dynamic system uses a set of differential equations to simulate the helicopter's behavior in real time. These equations capture the physics of the helicopter's motion, including factors such as lift, drag, and the effects of the rotor's rotation. The equations form a complex network, each one corresponding to a different aspect of the helicopter's behavior. For instance, one equation might describe how the rotor's speed affects the lift, while another could model the relationship between the control inputs and the helicopter's pitch or yaw. But how do these equations work together? Well, they're all interrelated. Changes in one factor can affect others, creating a ripple effect throughout the system. This interconnectedness is what makes the dynamic system so powerful. It can accurately predict the helicopter's response to a wide range of conditions and control inputs, from gentle breezes to gusty winds, from a slight tilt of the controls to a full-on spin. Interestingly, the dynamic system isn't just about predicting the helicopter's movements, it's also about optimizing them. By tweaking the parameters of the equations, the system fine-tunes the helicopter's performance, ensuring it responds quickly and smoothly to the pilot's commands. In a nutshell, the dynamic system is a mathematical genius, masterfully orchestrating the helicopter's movements and reactions. It's the invisible conductor, guiding the helicopter through the sky with precision and grace. And there you have it. The dynamic system is the final piece of the puzzle in the helicopter total algorithm. It's the unseen force that brings everything together, making the magic of flight possible. How do these components come together to form the helicopter total algorithm? Well, let's dive into this fascinating integration. Picture in your mind the rotor, control, and dynamic systems as individual players in an orchestra. Each has its own role, but when they come together in harmony, they create a symphony of helicopter flight. Firstly, the rotor system, it's like the heart of our orchestra. It generates lift and thrust, allowing the helicopter to ascend, descend, and move in any direction. But it doesn't work alone. It relies on the control system, our conductor, to dictate its speed and angle, transforming the raw power of the rotor into precise, controlled motion. The control system, in turn, relies on feedback from the dynamic system, our attentive audience. This system monitors the helicopter's motion and position, feeding this data back to the control system. It's an ongoing dialogue that ensures the helicopter responds appropriately to the pilot's inputs and the surrounding environment. Now, these systems don't operate in isolation. They are intricately linked, each influencing and being influenced by the others. In the algorithm, this interaction is represented by mathematical equations. These equations model the relationship between the rotor, control, and dynamic systems, integrating them into a cohesive whole. This integration is where the magic happens. It's where the helicopter total algorithm transforms from a collection of individual systems into a full model of helicopter flight. It's like the orchestra coming together in harmony, with each player contributing to the symphony. Each system, each equation, each interaction, all coming together to create a beautiful, intricate dance of physics and mathematics. This dance, this integration, allows the helicopter total algorithm to accurately simulate helicopter flight. It allows us to predict and control the helicopter's motion, to understand and explore the complex world of helicopter flight. With all these components working together, the helicopter total algorithm can accurately model and control helicopter flight. And that, my friends, is the power and beauty of integration. It's the symphony of helicopter flight, brought to life by the helicopter total algorithm. We've seen how complex and intricate the helicopter total algorithm is. It's a true marvel of engineering and mathematics, where different components come together to perform a symphony of flight. The rotor system, the literal and metaphorical propeller of the helicopter, plays a vital role in lifting and directing the vehicle. It's a delicate balance of physics, ensuring the blades spin at just the right speed. Then we have the control system, the brain of the operation. It's responsible for adjusting the rotor's angle, controlling the helicopter's movement in every direction. The dynamic system, on the other hand, keeps everything stable and balanced, compensating for the forces and torques generated during flight. And lastly, the integration of these components within the algorithm, a seamless fusion that allows the helicopter to hover, ascend, descend and move in any direction with the utmost precision.